And StreamYard says we are live. We are just going to wait for Twitch to wake up and see if it's true. It seems to be true. We are live. Welcome, everybody. Happy New Year. Welcome to this Ubuntu on Air stream. This is a community stream. My name is Yannick. I'm the French guy from Switzerland. And I am joined once again by Andrea, because we started a series about, I don't know, 4-6 weeks ago, before the vacation, last year, anyway.
Last year, yes.
About kernel programming, where, if I remember correctly, we started by with writing a bootloader, and we ditched that and used grub instead. And then you wrote a little bit of code that grub loaded, and we printed stuff on screen, and that was awesome. So first of all, how are you, Andrea?
I'm fine. There's a lot of work to do. Like, I hope I won't add too many bugs today, because my brain is a little bit like I spent the whole day debugging S390X assembly, so I'm like
yeah, I have heard that there's a new kernel in town.
Yes, the 5.15. We're trying to fix the latest bugs. Hopefully we will have kernel in release in Gemmy 5.15. Like, I'm hoping next week, actually. So
cool.
Yeah.
But tonight we're not going to write kernel 5.15. We're going to keep adding to the very tiny small kernel you started last time. So what do you have in store for us today?
So yeah, I would like to resume from where we started, where we stopped last time, and keep going. Like, we got to the point where we were able to like print K hello world or print K any string. And it would be nice to see if we can get to the point where we can try to do some kind of multi-threading, or even a scheduler. I don't think we can get to the point where we can implement a like true scheduler, but we can try. We can try to see how far.
We can try.
Otherwise, there's the episode 3, you know.
Exactly. If we have enough people interested, then we're gonna have to make episode 3, 4, 5, the whole series of.
And if people have questions, I'm really happy to interact and do. Or if they have special requests, like, can we do this? Can we do that? Yeah, that's totally cool. It's going to be like some live coding improv. So
there is a thread on Discourse. Let me try and get the link. I will get that while you start doing some code. So do you want to show the terminal now and dive into the code? Yeah. Okay.
Sure.
So let's add that to the stream. I will make that full screen, like that.
Okay, I'll try to make it bigger. Is it big enough? I think so.
Yeah.
All right. So last time we wrote the boot. This is the very beginning of the kernel. It's what the bootloader is loading as grub. And I just opened that, and I noticed that we added a bug. So I was like, first of all, I would like to fix this bug. Because I'm not sure if you remember, but we were trying to see how the C code is connected to the assembly, and to do that, we did like a push an address and a push number. These are going to be the argv and argc, the usual arguments that Maine is receiving. So, and that was working. But where's the bug? So this is supposed to be a dead end code. Like, if we return from main, we need to be stuck here. And this is what happens because we disable interrupt with this CLI, and we halt the CPU until an interrupt is received. But we're not going to receive any interrupt because we just disabled interrupt. So it's working. But where's the potential bug? The potential bug is here. Like, if we get a non-maskable interrupt and the CLI is not preventing non-maskable interrupt. We're going to jump back to entry, but entry is going to call main again, and I don't want that. This feels like almost like a reboot, like a soft reboot. What I want instead, if you get stuck here, so like, I don't know, dead, and
Okay,
jump.
so if we were to get out of alt enough time, we would like push things on the stack, and we would eventually have a stack overflow.
I also thought about that, but it's actually not the case, because like main, if we go to main, where's main? There we go. When main returns, it's calling, it's calling a return, and the compiler is doing the pop and pop these two. We can check that actually if we go objdump main.o. If we search for main, where's main? There we go. Main. If you see, it should do pop.
Yeah,
but I was expecting 2 pops, because we are doing push and push. So that's interesting.
So we're pushing twice and we're popping once.
Actually, no, because it's you see EBX is pushed up here, and here's the pop. So somewhere it should do the let's see if ESP. Oh, it's probably modifying ESP directly.
Okay.
I can't see it right now. Maybe it's doing something like that.
Okay, so we wouldn't have a stack overflow, but we would see our line printed again and again and again and again.
Yeah, actually, I think it's the caller that should do the pop. Like pop X and pop, something like that. Because I don't see in main. Yeah, at the end is just doing a return, and return is just popping the instruction pointer and jumping to the instruction pointer.
Okay.
It's not doing the. So I think that's safe.
So you need to clean after yourself.
Yes, exactly. Let's try to do a run just to see what happens. If it's still working. So
yeah, cool.
But even if you're like messing up with the stack, it's gonna work, because we're doing nothing basically. So like after returning from main input.s, we're just hitting the dead end. So
okay, yeah.
But anyway, it's good to fix that. So let's keep it like that, just to make sure everything is properly balanced. So another thing that I just noticed. So sorry, I'm not planning anything. I'm just improvising.
Yeah, best way to do it.
Yeah, another thing that I just noticed is that when I start the kernel, okay, you see that there's hello world and printed just fine, but the cursor remains in the first character. What I would like to do is to like advance the cursor to the end.
Okay.
It was a proper, console. So I don't remember where we implemented the console driver in main.c directly, I think. Yes.
Yes.
So we also recap what we wrote. We defined some helper types. So we can use a uint 32, uint 16, and 8 or 64. We defined this is the beginning of the console address. Then what we have, console buffer, position. Okay, position is where the cursor should be, right? Okay. So let's do. Okay, let's move the cursor. I want to move the cursor every time that a character is printed. So I want to, like, I don't know, update cursor like here, and And then we're going to implement update cursor. Do I want to pass a position? Maybe not, because like I can just use the global variable console pause instead of passing position, just because it's just easier. And let's see what. So the thing is that I need to program the console doing so. I'm going to show you something new that is very architecture dependent. This is like how Intel architecture is, how the architecture communicates with devices. You can write in memory, so that there's going to be shared memory like DMA or something like that. But there's also, in addition to memory or memory mapped I/O, there's also the concept of ports. Ports, you can output some data, bytes usually, to some ports, and you can input, basically it's writing and reading, writing to ports and reading to ports to communicate with the devices. The console, like specifically the cursor, is one of them. So I need a tiny little bit of assembly, and I'm going to define something. Let's do that in line, just because it's fancier. I'm going to call out B. That is the. So whenever I can, I try to use the same functions that Linux is using, like using the same names. Because what's the advantage? The advantage is that if one day I get to the point where this kernel is like complete enough, if I'm using the same functions or the same ABI, let's say, I could potentially just copy paste a driver from Linux and just
interesting.
Import the code here, and if I'm using the same function names, I can just compile and it should work. So
if you were to add a graphics card to Pastabot, you could just copy paste the driver from Linux.
Yeah, exactly. Okay, it's a long path to get to that point, but it doesn't cost anything to call function. For those that I remember to call function, those that are generic enough, I'm going to use the same name. So, and the same syntax. So this is how Linux defines the output port, and there's also the corresponding input to read. You specify the port. That's the first argument, and it's a 16-bit value. And the value that you want to write, it's a byte. So, and here I just, there's no other way. I need to do some assembly. And let me see, the assembly is going to be out B. That, so interestingly enough, the Intel instruction is called in the same way that same name that I used with the function.
That's easy to remember.
Exactly. And then I can do I don't know. This is going to be first argument. So it's interesting because Linux is, I don't know why, but it's doing this. It's using first argument is the port, second argument is the value. But in Intel, the first argument is going to be the value, and the second argument is the port.
Okay.
So there's this. And that's because it's like in assembly, it's the left operator goes into the right operator. So
okay.
This is why. Anyway, and then I need to, let me think, port, and maybe I'll explain if that works. Yeah, that's correct, because what I'm saying is that I'm moving this prefix A, means that value is going to be put into the AX register, or in this case AL, because it's a byte operator, byte value, sorry. And D is going to be DX, and it's going to be the port. So this is the inline assembly syntax, the GNU inline assembly. Basically, I'm saying use two registers so you don't have to move stuff around. Just use DX for the port, AX for the value, and I can use them because they are general purpose registers. And the fact that I specify the registers here, then the compiler knows that I'm going to use these registers inside this function. So if it needs to reuse the same registers, the compiler will take care of saving the registers, like pushing them on the stack when the function is called. Or if it's inlined, it will likely not push anything in the stack and just use the registers. Oh, we have Monica in chat. Hello, Monica.
We have Monica. Good evening, Monica.
And Happy New Year. All right. So another thing that I use is the video, or let's say console CRT port or console port. Let's do this. And I need to check because I don't remember the number. It's this one. 3D4 is the port, Intel port defined for the console. So update cursor is going to be something like that. Console port. I want to output, first of all, this is the base register. So the first register, I'm going to add +0 because I need to use the first register and second register starting from this address. And the first register, I need to check it needs to, yeah, it wants 14. This is just how the driver, you should check the data sheet and see that, and see what numbers it's expecting to receive. And in the first register, I need to put the upper value of the position. So console pause, right shift 8. So basically I'm getting the highest byte. And then I need to do, sorry, this is a bit complicated, but it's just how the driver works.
I guess that's it's done once, then you don't have to worry about that anymore.
Exactly. So once it's written, it's not really complicated. You need to output 14, and then you need to send the highest byte, then 15 and the lowest byte of the position, because the position is 16 bits. Even if we define the position as an integer, but it's just, we're going to use just the lowest 16 bits, and that should be enough to update the cursor. So
just a quick question. Earlier you said that's architecture specific, so that works on a PC. That will not work on anything else.
Exactly. That's the problem in this case, because we just define that we're going to support only Intel. It's easier, and everybody can run this code on their computer. So this is how Intel works. Unfortunately, Intel is a little bit convoluted.
So this is how it worked since, I don't know, 1970, since the first CGI graphic card. What was before CGI even? That was not even CGI.
In the old days of DOS, like DOS was running in 16 bits, and it usually in the interrupts, calling the BIOS directly to move the cursor. In this case, we are using, this is the 32-bit way, so it's the little more advanced version.
Okay. So
we are
in 1980s.
Yeah, 90s probably, because 32 bits was Windows 95 at that time. And even Windows 95, it was mostly like, there was still some 16 bits code lying around. But for sure that the graphic part was 32 bits. So that was, 1995.
And this is going to work for ages again.
Oh yeah. And that's because like they need to support this forever. So unless Intel changes policy. So anyway, that's it. Like this function and this function. Now the question is, do I want to update the cursor like every time that I print a character, Or probably this would be more efficient. Like every time that I print a string, I only update at the end. If I would do this, it's a little less efficient, but more precise, because every time that I print a character, I will advance the cursor.
Well, to be fair, we don't even see the characters being printed one after the other. We just it's so fast. We just see the string, so you could just update that at the end of the print of print key.
Yeah, exactly. So this would be better if I guess it's a matter of what I want to export to the external. Like, do I want to export print car also? In this case, I need to update the cursor, because if something else is calling this function, I want to also move the cursor.
Yes,
but if I'm going to export to the external or only print k, like this is not going to be static, I guess, because I may want to call print k from everywhere in the kernel. So if this is going to be static and restricted to the namespace of the console driver, this is a reasonable implementation. If I want to do this and provide also print car, I probably need to do this. But
okay, let's do that.
But I mean, this is print car is not even standard. I think the Linux way is called kput char. So we could do this maybe kput char.
Because kput char is way more.
Yeah, it's
nice.
No, it's basically like optimization,
Okay.
But in our case, I guess it's fine. This, just do print k and update at the end.
We'll leave the audience decide which way they want to do by forking the repo. We will put the links to the GitHub in the chat. I can actually do that while you keep coding.
Okay. Yes. Cool. Okay. So theoretically, that should work already. So if I recompile now, another thing that it's bugging me is this warning. I want to remove this one. And there's a trick. I want to show that it's a GCC built-in, so nothing special. But if you do like this attribute unused, it's quite complicated with all these underscores. But this is in this way you're just telling the compiler, like, dude, I don't bug me anymore. I know this is unused. Please stop saying that. So if I do make, okay, now I don't have. Let's do make clean and make. Cool. No warnings, nothing. So now if I run the kernel, let's see. Before there was, remember there was the hello world and the cursor was at the beginning. Now if that works, I should see the cursor at the end, unless there are bugs. Let's see. Yeah.
Yay.
Okay, now it's a better console driver. Cool.
Victory.
So should we commit this? Let's do the commit. I want to add only main, because there was, the input.s, there was a fixed bug in dead end code. And now we have console. I don't know, manage properly advance cursor, something like that. Cool.
Bug fixes and performance improvement.
Exactly. So any questions so far? Will this run snaps?
Of course it will. It will actually run flat snaps, because that's what we're gonna invent, that flat snaps.
To support snaps, well, in general, we still need to implement our kind of user space support. Right now, there's only kernel space. So to support snap, we should port snap in kernel space directly. And it's going to be problematic with the system calls that snap is doing, because we need to find a way to recompile snap and dynamically map the system calls to some. some
why
function.
don't we start small, and just have a few things? We'll see about snaps and flatpaks when, episode 375, when we get there.
Yeah, that's a better idea. And then there's a whole infrastructure of features.
So
More.
we could take a moment to say hello to our newcomers. The Destroyer Greg, Caffeinated Linux is in the chat. And Greg asks, I probably can do that. What's the project today, guys? Well, this is the second part of what is now a series, because there are two parts, maybe more to come, about writing a Linux kernel, or a kernel. Well, it's not Linux yet.
It's pretending to be Linux compatible, like we were saying before. We're trying to name functions use the same name that Linux is using.
Yes, and we've called that the Pasta OS because reasons. And if you want to know why we're calling that Pasta OS, if you want to know what is or who is PastaBot, you need to go to Andrea's Twitch channel, where he plays violin and also has a nice little robot in the background. So that's why we call that Pasta OS. Monica, if you could paste a link to Andrea's channel in the chat, thank you.
Oh, Kamal, hello. Also, there's also Kamal here. Unix compatible.
Hello, Kamal.
Yeah, exactly. All right, so
Unix somewhat compatible.
Yeah, to a large degree, yes. Let's say Unix compatible.
Well, it's got print K.
Yeah, it's got print K so far.
So that's the start.
Let me show again. You can print K hello world. Check this out.
So we have a kernel that can print a string on the screen, which is actually a big step.
Exactly.
From last time we had nothing, and you started from scratch, and now we have a something that can be started from the bootloader and does actually interact with the hardware. So that's cool.
It's like it's running natively on the hardware. Like there's no system call, like nothing else. It's just standalone. It would be cool that at this point, if you have a program that is only doing computing power and printing, you can already use this as a template to implement your own, native program that is running kernelless. I don't know, without the kernel.
Yeah, because we talk about kernel and stuff like that, but actually that's a program. The kernel is a program,
and
it could be the whole thing. It could be a computer could boot on that and do stuff very fast, because there's nothing else interrupting it.
For example, a good application to this could be a number crunching program. Let's say you have a program that is trying to crack some password. That would be ideal, because you don't have interrupts for now. So it's just doing straight CPUs, no interruption whatsoever. There's no paging, so you don't have the overhead of page faults, but because the memory paging is disabled, and so it's going to be really fast if we do like a big number crunching program here that is not doing I/O except for the print K, like cracking password. That would be way faster than the Linux. So
Monica says have it crack Wordle. So give it like it's that what 5 letters, 6 letters word, and try to find the word in the combination. I think it's something like that. I don't know. I've seen people got crazy about Wordle, but I haven't dived into this craziness just yet.
Yeah, I see people are tweeting there are many tweets or speaking about that in general. But anyway, so another thing that I noticed that I want to fix is the fact that we didn't specify the stack pointer. Like we're just relying on grab, because grab is setting the stack pointer to a certain position, mapping some memory that grab knows. What I would like to do in in our kernel is to define a place where I want to define the kernel stack. Because I'm thinking about the stack because we were saying before that the plan for today would be to implement threads. And a thread is defined as an entry point and a stack. So some code and a stack. So for the main kernel thread, I also want to define a precise position where I want to put the stack. And I want to show you an interesting way of doing it. So instead of coding, like allocating the stack, because I don't have a memory allocator at this point, I still need to write that. So I can't use malloc. So how do I allocate a stack? One way is to put that directly in the linker. So let's say I want to create a stack that is, I don't know, one page, like 4K, even if we don't have paging, but let's think in terms of pages because later on we're going to implement paging. We are already thinking in terms of pages. So page size, I can just hard code that because I know it's 4K, 496 bytes. And let's say that kernel stack size is page size. So where do I put that? I can put that in one of these sections. So text is going to be the code. And of course, I can't allocate the stack in the code because otherwise
that could do interesting things.
Yeah, you can. It's a way of injecting code in the stack, or actually it's the opposite, injecting stack in the code. Odd. I could move the stack into the data, and right now it would work totally fine. But data is usually it's better to keep it. So data is as initialized variables, and the stack is usually uninitialized. So the ideal spot is the BSS section. And so we have two options. We can put like the stack here after the area of uninitialized variables, or here before. This is just, it doesn't really matter. What I'm thinking right now, do you have any ideas? What do you think is better to?
I don't know. Can you remind me what BSS stands for?
So BSS, if you, I'll show you. Main.c. Let's say, do we have any variable? Okay, here. Look, console position is not initialized.
Yeah.
Right? So this goes in BSS. Console buffer, even if it's a pointer, but it's initialized to something. And console address, this is B8000. This goes into data.
Okay.
And why we have this difference? Because when you boot the hardware, the memory contains random data. So if you have all the initialized variables in the same section, when you load the program, you just load the initial values of all the variables, and you're fine. But if you have uninitialized variables, it means that you don't care about the initial value. In terms of security, it's still better to set everything to 0. But potentially, if you care about performance, you may want to accept the fact that you don't want to initialize them. So this is why there is a separate BSS section, a separate area of uninitialized variables, because it's up to you. You can decide to mem set the entire BSS section to 0, and that would be totally fine. Or you can just keep as it is. Instead of setting the memory to 0, you just, the memory from here to here is BSS. I'm not even touching the memory, and it's faster to load in this case.
Okay. But when you later assign a value to that variable, it doesn't move to data. It stays in BSS.
Yes, it stays in BSS.
Okay.
It's only
just for initialization.
Yes,
initialization.
Exactly. Only when you start the program, and that's the same for the
Gotcha.
regular executable files in Linux, like the ELF or the exe in Windows. The BSS section
You
is
said the W word.
well, it's in any operating system. Like every program has a code,
Yeah.
data, and BSS.
Okay. Gotcha.
Okay. So we were saying the stack goes into BSS because it's uninitialized. We can put this at the beginning or at the end. I would like to put the stack at the beginning. The reason is that, we're going to have like stack end here and stack begin, whatever, here. And this will be like the page size. Actually, no, it's the opposite. Sorry. Begin and end, because the stack goes backward.
Yeah, that's what I was going to say.
Decrement the stack. So that's the beginning and that's the end. I like to put this here because so we're going to start here and we're going to fill the stack up to the end. If we overflow the stack, if we smash the stack by doing many pushes, we're going to hit the data section. And usually, like if we're going to implement any kind of memory protection, this is a segment and this is another separate segment. Considering that we have two separate segments, we may want to, in this way, we are able, if we want, to implement some kind of stack protection, because when we hit data, it's a separate segment. So we can say, no, fault. Mm-hmm. Instead, if I do the opposite, if I do this, and I overflow the stack, I'm going to hit the BSS that is the same section. So I don't have an immediate way of implementing like memory isolation. I'm just going to overwrite the BSS section and random things can happen. I can
by random, you mean interesting things can happen? Like hours of debugging, wondering why it's not working. I know.
I can still implement some kind of protections by mapping this to two separate pages, for example. But the more layers of protection you add, the better. So okay. And it doesn't cost anything. So let's just do this. And another thing that would be interesting to do. So this is already aligned to page size because it starts at 1000. That is like 1 megabyte, if I'm right. And here I can do something like this align page size, and also this. So all the sections are aligned to a page size. So in the future, if we will ever implement some kind of paging, I already have all the sections aligned to page size, so to separate pages. That's good. And so how do I allocate the stack? Well, I can simply do this, use this syntax, kernel, how did we call that? Kernel stack size. Or I can do just page size, But actually, let's do this, because if I want to use like 2 pages or 3 pages, it's better. And yeah, that's it. We can even do realign also here, just to make sure that the BSS section is just in a separate page even more. So we have the code, the data, it means initialized variables. And we have the stack, and we have the section of uninitialized variables, everything in a separate page.
And the size of those sections, they will be decided by the linker. The linker will, at the end of the link phase, will decide that it needs that many bytes for the data, that many bytes for the BSS section.
Exactly. It's the compiler and the linker. They know, how big is each section, because they knows where each variable, each symbol goes. So yes, it's up to the linker at this point. So we won't see any change if we run the code. Like what I need to do is to say, so because this is stack begin. Well, let's call this like kernel stack begin and kernel stack end. These are actually symbols that I can use in my code. So if I do like here, move kernel stack begin in ESP, this is the stack point register.
Okay.
Let me see, is this correct? Yes, kernel stack begin is here. Then when I do a push, I go up. So that's it. This is how I allocate. I can allocate and initialize the stack. Another thing that I need to do if I want to be extra picky is to say kernel stack begin is an external symbol. It's not defined here. And that should work theoretically. Okay, at least it compiled. Let's see if it's still printing hello world. Still printing hello world. So yes, and we use the stack because we have done this.
Okay, so now we are no longer relying on grub allocating stack for us. We're taking things into our own hands, and we're getting we're master of our destinies.
Exactly, precisely. It's the bootloader initialized the bare minimum. Then it's up to us to decide because for example, I don't know how big the stack is for grab. If I want to use like 10 megs instead of one page, I can. I just need to go in my allocator, that in this case is just the linker. It's a static allocator, static meaning define at compile time. and I can change this. and I want, okay, this is something that I want to point out to something here about kernel programming in general, because that we don't see when we do user space programming. So for example, Linux, if I remember correctly, now there's the stack size of the kernel, like any kernel thread, is quite big because I think nowadays it's 32K or 64K even, depending on what config options you enable. But some time ago, it used to be 8 kilobytes, so 2 pages. That means that if you have many nested function calls and you allocate a lot of data in the stack, like if you have functions like these, like, I don't know, char data 10,000.
Yeah.
Okay, that's really bad if you do that in the kernel, because it means that the kernel used to have a limit of 8K for the stack. If you allocate 10K here, you're gonna overflow the stack. Stack overflow. So and it's really hard to catch unless you have some kind of stack overflow detection mechanism. So that sometimes I remember I fixed many bugs like this usually in wireless drivers or stuff like that, and it was really nasty because all of a sudden the kernel was starting to do crazy things and in random places. So it's really hard to catch when there's a bug like this, because like the problem happens here, but so the stack is actually smashed here, but then you jump randomly in the other parts of the kernel, and because you corrupted some memory, you have random errors, and good luck at finding where initially the problem was introduced.
So in the example that you gave before, the linker file, if we were to overflow the stack, then we would change values of initialized variables. Is that correct?
Yes,
we could do that if we were to hit the area of data that contains that. So suddenly our variable changes value and we don't know why.
Yeah, exactly. Yeah, let's say if I do this, like char data, let's say so it's page size. So if I do I do page size, exactly page size, I'm wondering what happens, because C is going to be defined, it's going to overlap with the string, because the string is, where's our string? The string here is also a variable that goes in data. And I don't think we have many initialized variables. So if I do something like this, probably nothing happened, or I'm going to corrupt this string. It depends if I'm lucky or unlucky. We can try to do that. Let's see what happens. Okay, unused variable. Oh, because it's unused, maybe the compiler is smart enough to say to just ignore that. But let's see. Yeah, it's still working. Probably because it's an initialized. So I should do something like that for I equals 0. Size of data I plus plus data I equal I don't know, but let's try to do this.
But that's one of the problem with those kind of things. They are hard to debug, but they are also hard to actually reproduce, voluntarily reproduce.
Exactly. Make
so
run.
Monica says, oops,
Right.
that's not the one I wanted.
It's still good. The compiler is smart enough.
The compiler knows you're up to no good.
Oh yes, let's obj like Kamal suggests. Let's see if it's actually doing something. Oh, hold on. Let's do this. 5 less. Is it actually allocating? What was the function? Print k.
Print k.
Is it actually doing? Oh yes, it's doing some move. Let me see. I think it. Yes, incrementing ECX looks like my 4.
Yeah.
Incrementing I. Testing. Oh, it's testing the L. It's hard to decode, but this is probably the fact that there's a move. That means it's moving. It's moving into my stack. Like it's writing stuff in the stack. So I think we're just being lucky, and we didn't hit the anything in data. Let me see. Here is BSS is here. Yes, data is linear. Yes, exactly. So the linear address is the physical address. This is 1 meg. 1 meg and 1k. 1 meg and 4k is the BSS. And data is 1 meg and 100 in X. So my stack is going to be between 100, 100 and 101, 000, something like that. Let's say Kamal is saying obj-t will show where your stack symbol ended. Oh, thank you, Kamal. -t. Let's see. Boot entry.
Yeah.
Okay, kernel.
1 meg and 4k.
Oh, look at that. It's 1 meg plus 4k. And stack begin is 1 meg plus 8k, and that's correct because it's like, oh, so I need to stack end. Maybe I need to allocate like 8k. Let's see what happens.
We're trying very hard to crash the very tiny kernel we wrote.
It's still working. I don't know.
That's the most robust kernel I have ever seen.
10k. Oh, is it 10k? Let's try random data, because why not? Oh, it's still working. Yeah, I don't know. Well, anyway, that's another exercise for next time, or who wants
which proves that it's, as I was saying, it's hard to debug, but it's also hard to voluntarily crash.
So. Yes, that's probably something that they were missing here. Yeah, I don't know. I'll we'll do next time. I'll try to see
next time we will crash the kernel live on stream.
Mashing, yes, and such. Okay, so we have the stack allocated properly, so we can. Oh no, wait! Did I remove? I removed too many things. We need char c. Okay, cool. Make run is still working. Yes.
Okay,
Git
cool.
diff, git commit, kernel allocate main kernel stack. I don't know, something like that.
Yes.
So we will have everything in git log. Okay. Next thing, I would like to see if we can, I don't know, implement something like a scheduler. Can we do that? I don't know.
Of course we can.
Any questions so far?
So far, no. I didn't see any question, but feel free to ask your question in the chat, either YouTube, youtube.com/ubuntuonair, or Twitch, twitch.tv/ubuntuonair. And either now, or if you don't have time, or you think about something later on, there's a discourse post for this series, and so feel free to go on discourse. And I have the link here, and there we go. And yeah, ask your questions there, and we will do our best to answer them. Well, I'm just going to read the question, and Andrea is going to answer the question.
If I know the answer, okay. All right. So we can start with a scheduler. Well, a scheduler. First of all, we need to implement the concept of context switch. Context switch means that I want to be able to find different threads or different tasks in my kernel and switch between them. First of all, okay, to do a proper, like a real preemption where kernel threads can be interrupted, we need an asynchronous source of interruption. That would be the clock. That would be interrupt. But we still need to implement the interrupt manager. So we're not going to do, we can't do that yet. But what we can do is we can implement a kind of, we can implement a voluntary preemption model, meaning that the kernel can decide directly when to release the CPU and do like a yield to another kernel thread. And by the way, this is actually how, if you install the generic Ubuntu kernel, the generic Ubuntu kernel is using a voluntary preemption model. So the user space, of course, can be interrupted anytime. It's fully preemptible. But the kernel space cannot be interrupted except when it voluntarily releases the CPU. If you want a fully preemptive kernel, you need to install the low latency kernel. That's something that like not many people knows, but
yeah, someday we're gonna have to have a stream dedicated to the differences between the real-time kernel, the low latency kernel, and the generic kernel.
Yes. There's a lot of misconceptions about real time because the usual complaint is that, hey, I installed the real time kernel, but it's going slower. Yes, of course.
It does. That's the point.
The real time is not fast. Real time is slow and predictable. That's predictable is the keyword. It's not speed. And sometimes I say, maybe you want the low latency because you don't want to go fast. You want to be responsive. Yes, the system needs to be responsive. Then you need the low latency kernel, not the real time kernel. But anyway, that's another.
That's story. For another stream.
Yeah, maybe in a next episode we can get to the point where we do a fully preemptible kernel, and we can show what happens if we change like the frequency of the clock. Like how we can do like a more server-oriented kernel versus a more user space desktop interactive kernel. Those things.
That would be interesting. Yes.
Yes. Okay, so I'm going to define as cat.h, or should we define everything in main? Let's define everything in main so far, because then we're going to split in multiple files. But it's cool to have everything in one file. So for now, so let's do like scheduler, another section. Because I want to use a single file for now, because then I want to show like, look, we have console driver, what we have, print K, scheduler, and main all in a single file. That, you know, that when we say C is not compact as Python, well, it depends. Maybe we can. It's not, but okay, we can try. All right, so first thing that I need to define a task structure. And I'm going to use task struct as a name for the same reason that I was saying before, because Linux is using task struct to define the object, the task object. So what I need, I don't know. I need an entry pointer. For now, let's say the entry point of a task is just void. This is a pointer to a function. Not sure if you're familiar with this syntax, but it's basically I can define like I don't know, task one entry point, and then I can pass task one entry point as a value for this attribute. But for now, let's just define the structure. So I need an entry pointer. I need a stack. Let's define the stack as an array of 32-bit values. Stack. How big? I would say, well, let's put stack size, and we define stack size like we have done in the linker, page size. And page size is going to be 4K. So this is basically what we defined in the linker. And so the main kernel thread will have 4K of stack, and all the other kernel threads will have 4K. So because why not? Like they fairness, they have the same amount of memory.
But do we have enough space in the stack that we have defined in the linker for that? Because if you allocate 4K for each thread, you need certainly you need more.
One way could be to define everything in the linker, but in this case, I can just rely on GCC. So let's say I can do like static struct task struct task one, for example. And this will be allocated. So because it's uninitialized for now, this will be allocated in the BSS section. So I don't have to explicitly define a section in. I could have done that even before without touching the link, like saying static win32t main kernel stack, something like that. I can do that and not touch the linker, and then I need to pass this symbol to boot.s. It's actually, but yeah, that could be a way.
So you would set ES, is that ESP? ES6?
Yeah, I can. And in boot.s, I need to do main kernel. You know,
so it doesn't have to be the stack as defined by in the linker file. So that I understand.
Doesn't have, but I don't know. I wanted to show also that way. It's something to be familiar with. It's nice. And I was missing something. So a stack also has a stack pointer, because I'm missing that. So okay, it's a pointer to a 32-bit value, and that's it, I would say. Yeah. Okay, one thing that this is just me being extra paranoid. But what I want to do this. Move entry point to the bottom. Because I think in terms of optimization, this is going to be, stack is going to be a page. So I want the task struct to be aligned to the page, to the beginning of the page. Because if I do this, I'm gonna touch like the first 4K. Sorry, the first four bytes because you are in 32-bit space. So a pointer is 32 bits. I'm going to use 4 bytes, and then I'm going to use a page. So the last 4 bytes goes into another page. That means, okay, we don't have page faults, but
we could.
We could. So if I put the stack in the middle, I'm going to eat 2 pages, and I don't like that. In this way, if I'm using only the stack, I'm going to hit a single page. So I have 1 page fault instead of 2. And it's
also, if we overflow the stack, we would overwrite the entry pointer.
Yeah, exactly. That's another example.
Another level of protection.
I don't. There are little things, but it's good to make them properly because you have at the end you will see the advantages in terms of performance or security, or there's just little things. Okay. So I think we have everything. That is, this is going to be the object that represents a kernel thread, because we have a stack, a pointer, and an entry pointer. And I like to do this because from a logical perspective, it's better. Like we have stack related things and then code related things.
Okay.
What else? Okay, we have the stack. Now I need to create a task or a kernel thread or whatever we want to call it. I need a way to initialize the stack. So let's initialize the stack. Stack init, and I need to pass task struct. Let's see. Okay, to initialize the stack, I need to do move data in the stack. So task stack pointer. Wait, I need to, first of all, I need to initialize the stack pointer. So task stack pointer equal to task stack of what? Stack size. Actually, you know what? That's this is not correct. Okay, this is correct. If I want to be 4K, because I don't want stack size 32-bit objects. I want stack size divided.
Oh, okay. Yeah.
Divided by 4, and then in this way I have 4K. So
we've got 4K bytes, but we can store 1024 32 bits in the integers.
Exactly. This needs to be 1024, not 496, because if I define this as a char, then
okay.
But because I have defined this in this way, and we could do one way or another. It doesn't matter. So this is going to be.
And then we initialize the stack pointer at the bottom of the stack, and then we're going to go up. So we're going to decrement the stack pointer. Okay.
And in fact, we need to do minus stack pointer. So in this way, I move to the end, and then I'm going to decrement and set the value. That is going to be what? The entry pointer at the beginning, I would say. Task entry. Also, why the entry pointer? Because what I want to do is to implement. What I have in mind is to implement a kind of stack switching content switch. Basically, I want to. The running program will push everything, all the registers, general purpose registers in the stack. Then it's going to switch the stack, and it's going to pop the same registers. But if I switch the stack to this one that I'm creating, there will be a transparent content switch from a task to another. And entry pointer is going to be like as if I was calling a function. So it's the instruction pointer that would be naturally pushed into the stack when I do a function call, a regular function call. So the content switch at the end we're going to implement the content switch as a regular function call, with the difference that we are going to push all the general purpose registers and pop them back. And at the in the middle, we're going to do a move of the ASP register, the stack pointer, to the new, from the old task to the new task. And maybe it will work. Maybe, I don't know. Oh, Dark Dynamo, hello. Oh, good to see you here.
Welcome. Yes, we are doing live kernel coding.
Okay, so registers. I need to do the same for the register. So this is easy because it's just going to be 0. Let's say this is, let's put some comments. This is going to be EAX, so like the first general purpose register. This is EIP, instruction pointer. EBX, ECX, EDX, EBP, ESI, EDI. I know the registers. EDX, ECX, EDX, what did I say? EBP, ESI, and EDI.
Some of those registers, I remember back when I was doing some x86 assembly, there were some AX, BX, CX registers.
Because in 16 bits they were called this, and then in 32 bits they're called this, and in 64 they're called RRRR. This is 64 bit. This is how Intel is calling the registers. So this is like potentially it's a way to initialize the stack pointer actually and stack of a task. That should be enough. I may want to do like an helper function like static void. I don't know, task init. Let's accept task struct task and well, I don't know if I even need that, but okay, let's do int int entry void. No, why int? It was void entry. That's it. What we are doing here is just say task entry equal entry, and then task stack init task.
Cool.
Maybe we can just do, I don't know, task init and do everything here.
Yeah, we'll refactor later.
Okay, cool. Awesome. Okay, now there's the difficult part. Like, how do I implement the switch?
Yeah.
Good question. Okay, let's see.
I don't have the answer.
Okay, we're gonna we need some assembly now, because for pushing and we need assembly anyway, because I need to pop all the registers and a move of the stack pointer. So let's call this I don't know, switch to, and I want a struct task struct new task struct no.
Oops.
Yeah. Okay. Void switch fat-fingered everything. New struct task struct old. Cool. 1, 2 tasks. Let's move the stack pointers into registers. This is a trick. Uint 32t. Let's do old stack pointer. And I'm going to do something. Okay, I'll explain. I need the old stack pointer and the new stack pointer. Let me move this up so you can see. Okay, you can see. What I want to do is I want the address of the, because I don't want to. Okay, so the old stack pointer actually need to write into memory. If I do this, I will just update the register with the value of the stack pointer. Instead, I want to save into the memory area of the stack the current ESP register into the content of old stack pointer. Not sure if it makes sense why I'm doing.
Kind of, yeah. I'm
you can guess.
Following, yeah.
Because if I do this, I would save ESP in old SP. That is just a local register, and it would get lost. So if I get the address and I do content of old ESP, I'm going to save ESP directly into the memory area. So let's see. As volatile, I need some assembly here, and let's see what I'm going to do. Okay. First of all, push everything. Push long EAX. Let's do multi-line as inline assembly. EBX, ECX, EDX, EBP, ESI, EDI. Okay, and that's the same order.
Yeah.
It's the same order that we have here. That's a push. So yes, it's the same. EBX, ECX, EDX, EBP, ESI, EDI. Perfect. Now, we don't have a push, but I want to save the current stack pointer into the content of old SP. So move. Yes, because I want to save the old stack pointer into the process state. So this is going to be the content of the, let's so 0 and 0, 1, 2, 3 are going to be the arguments that I'm passing to this ASM volatile at the end. So when I do like let's say here's the end. I'm gonna put all the arguments here, and these are the outputs. These are the input, and then there's a keyword, the memory, that says basically preserve the memory barrier. Like don't compiler. When I say memory, I'm saying to the compiler, don't take initiative. Just do what I'm telling. Okay, don't do anything crazy. Just do what I'm telling you to do.
Don't try to be smart.
Don't try to be smart. I want exactly that. So
let the human be smart.
Exactly. And then I need to do like, okay, let's do 1 here and 0 here. And I need to move 0, not the content. This parenthesis means content. I don't want to move the content, but I want to move the value of new stack pointer into ESP. So you see what I'm doing? I'm saving the old one and I'm replacing the stack pointer with the new one. And then I need to pop everything in reverse order. So, oops, here, okay. This is going to be pop L, not EAX, but EDI, ESI, EVP, EDX,
yes.
ECX, EBX and AX. Okay, cool. We have the skeleton of our stack switch, context switch. I just need to put the right registers here. So this is the output. I want to move this into let me think. This one is 0 is going to be the new stack pointer. So let me do this. First, the input register new SP is going to be the new stack pointer. And I also want old SP to be another register. So the compiler, I'm telling the compiler that it needs to use 2 registers for this. And this is also defined by the keyword register here. So these are going to be 2 registers. 0 is the first one, new SP. That is the value that I'm going to move to register ESP. And 1 is going to be old SP in the content, and that's fine. But what I want is to equal our old SP. And just to make sure it preserves also new stack pointer, I'm going to put that new SP. Basically, this one wouldn't be required because I want to. This instruction here is writing in %1, so it's writing here in content of old SP. New SP, I'm basically saying don't do anything crazy, just keep the value with new SP as it is. Okay, I think I told the compiler to not do crazy things. Cool. The last thing that I need to do is return, because the last value in the stack is going to be this EID, the entry point. So basically, this is going to be a function call to entry point if everything works. And there are probably bugs, but we will see. I think that's it. That's the context switch. So, yeah, should we? I don't know. Any question? I mean, it's not easy to read, but
I think I understand that. Why don't we give that a try?
It's important, like, to get the concept. So then you can if you want to study exactly how it works, you can look at the code and understand. But the idea is, we push general purpose register stack switch. You can also do this, like push general purpose registers stack switch, and then we pop general purpose registers and return. Okay. Looking at the code, I don't see any bug. So hopefully
that's a good start.
Let's see if it compiles. Okay, so it's complaining because it's unused, but at least it compiles. And as Greg said, if it builds, ship it.
Ship it.
Okay. So let's define a kernel thread. Let's do static struct task1, and let's see, or T1. And let's do, I don't need to define the stack because it's already defined in the struct here. Okay, cool. Let's see. So let's define the entry point. Static void task1 void. We will implement passing arguments and returning values later in the next episode. Why don't we? Yeah, I will just do like print k hello from task1. How about that? Forever.
Sounds right.
And okay, well, okay, let me remove the, okay, I don't care. Let's keep hello world. and then we can do switch to. Oh, I need to define a dummy static struct task struct init task, like I need to define a structure that represents the main thread, because I want to move when I move the old stack pointer, the current stack pointer into task sp. Old sp I need a place, so this is going to be the dummy entry point. Switch to is going to be t1, good. Init task. And if that works, I should be able to see hello world, and then this guy is going to go crazy and print hello from task 1 periodically, like forever. So, let's see what we get. It's complaining. Task 1. Oh yes.
This is where we should. This is where we should play a commercial and say we will be right back.
Yeah, so I'm missing something. I'm not initializing T1, right? That task init. I'm never using task init.
Yeah.
I need to do task init address T1. Too few arguments. What I mean? Oh yes, I'm missing the entry point. Task 1. That should be right. So I'm initializing this structure with T1.
Yes.
Stack init is done inside task init. Cool. Make. Oh, no warnings. I'm scared. Make run. Let's see what happens.
All right.
Whoa. So yeah, we don't have /n implemented, so it's just printing.
It does work. So right now, if I understood correctly, it switched from main to the second task, but that's all it did right now. We're not interrupting task 1 just yet.
Yeah, but what I can do is I can do this. I can do the opposite. Init task. Hold on. T1. So this one should jump back here. Now I can do something interesting. Let's remove hello world and do while 1 print k
hello world,
hello or hello from Maine. I don't know.
Okay. And then we need to switch to it.
Actually, let me do this. It's better. So I initialize task 1 and then go from main. That it goes into this other task doing the stack switch magic. I should see hello from task 1 and then go back to main.
But you need to task init T2 or init task.
Maybe not.
Maybe not. Okay.
We can because I can do that init task, but actually I don't care because I'm only the first time I'm only writing into init task.
So the first switch will initialize the task.
Because what I care about init stack is the stack pointer. I don't care the entry point because the entry point doesn't exist because it's the Big Bang, is the source of everything.
Okay.
It doesn't have an entry point. I only care about the stack pointer, and the stack pointer is initialized the first time that it calls.
First switch, okay.
So I can do that and initialize. Do we have null? I don't think we have null. Let's define.
That's the thing with the kernel. That's what we were saying last time. We don't have any glibc or anything. So
you have nothing. So and if I don't do this, look, it says null. What is null?
Nope.
Yeah,
nope.
So I need to do this. There's also another error.
Computer says no. Axi is unused now. So
yeah, Axi is
because we used the Axi last time just to check that we did receive something from.
Let's
the
say,
kernel.
okay, don't bug me. But there's also T1 undeclared.
Yeah, you removed the. Oh no, T1 is there. It's
init task. Wait, init task is here. Why undeclared? Hold on. What if I do this?
they just declared too far down, says Kamal.
Oh.
Oh yeah, in task 1 you reference address of T1, so you need to move the static struct task struct T1.
Oh yes. Thank you, Kamal. So I need to do that. Actually, I want to do at the very top because this is going to be the scheduler. So, like here, I want to initialize. I want to have init task, and I can even do that, like dot entry equal null. I don't know. That would be the initialization because I don't know. Sorry.
Same thing with T1.
T1, I could. Yes, I could do that.
But you need to put it above the definition of task 1 because you're referencing T1 in task 1.
That's true, and I also need to somehow initialize the stack.
Yeah.
So I need to.
Okay.
I can do, dot entry equal task 1, and then call stack init, and remove init task init. We can also do that. Like I don't really need task init at this point.
Like that.
But I don't know. Let's.
Yeah, leave it like that. Leave it like that. Just move the definition of T1 above task 1. Otherwise, the compiler will complain.
Yes, that's good. Here,
yeah,
so
okay.
And that's fine because I define the task object, then I have the implementation, and
cool.
and initialize everything here. So that should be okay. Except that there's a syntax error. Isn't it correct? I think it's correct. Static struct dot entry null. Oh, maybe it's there. Yes. Okay. Sorry. Comma versus column. Okay. Make run.
Yeah.
We should be able to see like the main thread and hello from init and then hello from task 1. Let's see.
Sure.
Okay. We can.
Yeah, we can see things.
Can see some. Let's do. I want to do /n.
Will that work?
No, because we don't even have /n, but we can do something here. So,
so we need to
print car. It's in print car. If I need to do like a switch or something like that. See.
And then you need to update the console position.
Yeah, like case.
Okay.
Case /n. Do something. Default. Do this.
And then
break. Then, in any case, if console position is greater than 80 times 75, reset it. Yeah, this is an ugly driver because we were saying last time when I go at the end, it just jumps. It just move back to the beginning. A better way would be to scroll, like to advance.
Yeah, baby steps.
Next, okay, baby steps. Good.
Baby steps.
So this one, what I want to do, I think I need to do like console pause plus equal. Okay, let me define console width 80. Yeah, height 25.
Yeah.
Console width Is this correct? I think I need to do like because I don't want to increment directly. Okay, let me write. Maybe we can refactor later, but console. I want to move down, but also
move back to
yeah, I don't know how to explain, like console
yeah
in modulo, in this way I normalize
yes
it, go back at the beginning of the line.
yes exactly.
If I mean that should work. I'm not sure.
That
But
I agree. That should work.
okay, and do I want to update cursor? No, I don't care because I'm gonna use print k. So let's see if it works. Now that
Yeah.
we can see like hello from task one. No, yes, hello from task, actually hello from main, new line, hello from task one. Let's see. Make it happy, make run. Ooh, we see that. Look at that.
It works.
Awesome. We have a
Awesome.
multi-threading kernel. That's
That's great. So that's what you call the voluntary threading model.
yes,
So a
voluntary
task.
because of this, because it's the kernel that is
Yeah.
usually, we should have a like a sched field. This is how Linux would do that. It's called the scheduler, but we don't have the scheduler yet, so
So
we just call the context switch directly.
all
And
right.
and this, you can, like you were saying before, you can use this template to implement your own multi-threading program that runs natively in the hardware, and it's super fast because no interrupts, no paging, nothing, and you have a primitive to use to create tasks. So that's cool. And it's how big is that? Let's see. It's 13K.
13K.
Actually, if we remove the debugging,
Yeah.
let's see, how big is that? It's
8K.
8.4K. And
Cool.
running kernel with multi-threading, console driver, print K.
Excellent. Well, I think we're going to stop here for today, but we've just opened the whole lots of doors, so we can build on that. Well,
Yeah,
I was a little bit higher level than last time, I think, but it was really interesting. I mean, I'm learning lots of stuff. It's just basic programmation. It doesn't have to be kernel stuff. Actually, right now, it's basic programmation. Yeah,
exactly.
Thank,
It's kernel programming, but it's just C programming at the end.
yeah. Wow, that was great. And Greg says thanks for the great show and tell. Yeah, well, Greg, we should be back. I don't know if we're going to be back in 2 weeks with a third one, or if we're going to wait for a month or something. We'll figure out that in the coming week. But definitely, we're gonna have a part 3 and probably 4 and 5 and 6 about that, because I personally think it's very interesting, and I hope
We need to get to the
find
point where we can run like user space application. We can start to call
yes.
the programs.
Yeah, so that was one of the thing I had in my head for these past few days, is that so far we're inside the kernel space, but at some point we're gonna have to go to user space and make those two spaces talk to each other. So
Yep.
that's gonna be great. We'll keep you updated, as I posted the links already multiple times in the chat to the discourse post. So if you have questions, if you have requests, or if you want to tell us how bad we were or how good Andrea was, because I was just sitting there doing nothing, please don't hesitate to update the thread on discourse. And well, I guess the code is also on GitHub. The link is in
Yeah, I will
thread.
push code on GitHub. There's a branch.
So yeah, have a look at that. Send a pull request if you want to. And well, thank you very much, Andrea. That was very interesting. and I'm looking forward to the next installment of this series.
It sounds good.
Oh, someone just popped in the chat.
Oh.
Q Solutions. Hello.
Hello, thank you.
Welcome. We just finished, so we're
You can
gonna.
watch the VOD if you want.
Yes, there's the vote on Twitch. I think the vote is going to stay for a while, and on YouTube. Otherwise, youtube.com/Ubuntu on air if you want to watch all the previous videos. Well, thank you, everybody. Thank you, Andrea. Thank you again for joining us. Once again, Happy New Year, everyone. We will be back in 2 weeks, either with part 3 or something else. I don't know just yet. We'll keep you informed. Stay tuned. Have a good evening. Have a good week. Join Andrea on his Twitch channel if you want to hear some violin and see how Pastabot is annoying everyone in the chat.
Something different than kernel programming. It's
Yes, something a
more
bit
relaxing.
different. Indeed. And that's it for tonight. Thank you, everyone. Have a good evening. Cheers. See you.
Bye.
Bye-bye.